Yeah, now consider background correction in atomic absorption or emission. Okay, background is always there, so this background is a noise. So the noise level should be removed or should be minimized yeah, as possible. Okay, for example here, um, yeah, here background signal arises from absorption, emission, or scatter by everything in the sample beside analyte. Okay, analyte is the species of our interest, as well as from absorption, emission, or scatter by the flame itself. Flame makes noise, or plasma in ICP, or the furnace. For example, the graphite furnace. This is an example. This is the signal from graphite furnace. Okay, graphite furnace absorption spectrum of bronze dissolved uh, in nitric acid. Okay, here it shows a very nice peaks belong to lead and iron and copper. There are many iron peaks. Okay, but since this graphite furnace itself you know, itself generate some a signal, right? Look at that. These the peaks are not based on the zero signal, okay, but on the observance of point 0.3, right? This is always there, right? This is point 0.3. So this is the background. Yeah? In other words, this is the noise. Okay. So in the presence of this noise, the exact determination of the sample is not easy. Okay. So this background should be minimized. All right. And how do we do that? There are basically four method. Okay. The first one is the adjacent pixels of CID, charge injection device, display. And second one is beam chopping and use of deuterium lamp and Zeeman, use of Zeeman effects. Okay, let's consider one by one. First, um, the this one, the method of adjacent pixels of CID display here. And look at that. This is the signal. The blue line is a signal, and the x-axis is a pixel number in CID display. Okay, and as you see, this one, this middle, this peak is the real peak. Okay, but this peak, the background is not constant. Yeah? In this case, the background is very high, and this one and on a pixel number 14 or 15 the background is small. Okay, the signal is on pixel number 7 and 8. Okay, this is pixel. Okay, and so this is whole signal is the sum of a true signal and plus the background. All right, and so one way is to uh, take mean baseline. Okay, over here 1 2 and 14 and 15. Okay, so we take the average background, right? And the corrected peak height, right? This is not real peak height, because this is not background signal was not subtracted. Okay, but for this peak the background is not constant. It's what it's changing. Okay, depending on the pixels. Yeah? So one way to do it is that take the background on the left side, and then also background on the right side, and take an average. Okay, yeah. So corrected peak height is the mean peak amplitude. This one, these two. Okay, take a mean, and also we take the mean value of the baseline, and we subtract this baseline. Okay, from the mean peak amplitude. Okay, this is the one way, but this is not a very good way of background correction. Okay, maybe easiest one, but not very recommended. Right. And second way is to use beam chopping. Okay, this is called modulation. This is a very powerful technique to remove background, yeah, and also taking the signal only. Yeah? This modulation. You see, modulation has been very widely used. For example, for sending the signal over a very long distance. Okay, and for example, you know, the AM and FM. Yeah, AM means what? Yeah? You turn on the light. You can select AM or FM. AM is amplitude modulation, and FM is frequency modulation. Yeah, modulation is that you have a signal, yeah, but the signal is quite weak. Yeah, but if you send the signal itself, yeah, since that signal is very weak, and then it may be fade away while it is traveling to the to some place. Okay, and the weak signal is conveyed by other the signal, but that signal amplitude or the frequency are quite different. Okay, and anyway, so we carry the signal over our what another the wave. Okay, and then at the detector we only select the the signal frequency. Yeah, that kind of technique is called the modulation technique. Okay, and let's see how this modulation technique is used in atomic absorption or emission spectroscopy. Okay, here is the lamp. Okay, maybe hollow cathode lamp. Now, ordinary a atomic absorption spectroscopy, this lamp, hollow cathode lamp, light is directly passed through this flame. Okay, here on this flame, the sample is there. Okay, and but in this case, um, here is the detector, right? Detector contains uh, actually true signal and signal from the flame itself. Okay, flame itself generate the noise, right? The signal detector signal contains noise also. So there should be a way of removing that noise. Yeah. So using the one way is to use this beam chopper. Okay. This here this is a motor, and this is a motor blade, and but this motor blade, here is the this blade and empty blade, empty blade, empty. Okay, and then now you spin this motor. Okay, spin with a specific frequency, and beam now is chopped. Okay, look at that. This figure C. Yeah. When the beam hit this blade, there is no detector signal. Okay, only in this time period, the detector contains only a signal from this flame. Okay, why? Because this lamp light is blocked. Okay, so detector only detects noise, and then when the this is open, and then light from whole crystal lamp pass through here, and then is absorbed by the element of our interest. Okay, and plus and noise, right? Detector now contains both signal and noise. Okay, like that. In this period, yeah, we have the signal. Okay, yeah, like this one, right? So since you rapidly spinning this chopper, then this is a chopper frequency. Okay, and how do we select this only signal? Okay, yeah, there is a technique called lock-in amplifier. Okay, you don't need to know that actually. The technique is I have a long time to explain it, but idea is that here is the detector, and then this frequency is synchronized. Yeah, is synchronized by the detector signal. Okay, and then only the signal whose frequency is the same as this chopper frequency is detected. Okay, that is a kind of modulation technique. You understand? You see, this noise contains any the any frequency. Okay, but signal only contains signal frequency is the same as this rotating chopper frequency. Okay, you understand? Yeah. And then there is a technique to only select the same frequency signal. Okay, yeah, all right. And here detect a signal whose frequency is the same as the chopper frequency. Yeah? This is very important. Yeah? There is a very powerful technique. They call the lock-in technique. Other signals of different frequencies are not detected. Okay, so this signal, although signal is very weak by this technique, the weak signal could be very nicely detected. Okay, yeah, that's the beam chopping. And the idea of beam chopping is that beam chopping must be done right after the lamp. Okay, if you place this beam chopper, rotating chopper, after the flame, yeah, there's no use because the flame signal also modulated by this chopper. Okay, so basic idea, basic principle of using this chopper, yeah, is to place this chopper as close to the lamp as possible. Okay, that gives the best signal. Okay. Yeah, another method is to use deuterium lamp. Okay, from the figure, the previous chapter, we know already that from the deuterium lamp, it generates this wavelength signal. Okay, this deuterium lamp generates mostly near UV light. Okay, now this is rather broad compared to hollow cathode lamp. Okay? Broad emission from a deuterium lamp is passed through the flame in alteration with that from the hollowed cathode. Okay, this one is also alternately you send this deuterium lamp, yeah, to the sample. Okay, first hollowed cathode lamp light, and and then light from deuterium lamp and then light from hollow cathode lamp. Yeah, alternatively, okay, you pass those two light to the flame. Okay, the monochromator bandwidth is so wide that a negligible fraction of T2 radiation is absorbed by the unlight atomic absorption line. Okay, but idea is that this one light absorption, yeah, the sample absorbs the light, but light absorption from deuterium lamp is a very small, actually negligible fraction of T2 radiation is absorbed by the unlight atomic absorption line. Okay, yeah, yeah, it may be this light in, may be absorbed by other elements, but our only light absorbs a negligible fraction of T2 radiation. Okay, light from the hollowed cathode lamp is absorbed by only light. Okay, although it is not here. In hollowed cathode lamp, since the we use the same element, okay, to detect the element, we use the hollow cathode lamp with the same element, so the light from the hollow cathode lamp is absorbed, okay, strongly absorbed by other light, okay, and scattered by background. Okay, yeah, light from T2 lamp is absorbed and scattered only by background. All right, because the other light absorbs a negligible fraction of D2, only the D2 lamp is light. D2 lamp light is absorbed and scattered only by background. Yeah, that's the idea. The difference between absorbance measured with hollow cathode lamp and absorbance measured with T2 lamp is the absorbance of an light. Okay, so yeah, so true signal is the hollow cathode lamp signal it contains sample and background, minus D2 signal, it contains only background. Okay, this way we only select, okay, the true signal. Okay, yeah, that's the another idea. Okay, next idea is Zeeman effect. Zeeman, pronounced Zeeman effect. Zeeman is a person's name who discovered this effect. Yeah? Let's consider what the Zeeman effect is. Okay, Zeeman effect is the splitting of a spectral line into two or more components of slightly different frequency when the light source is placed in a magnetic field. Okay, here you pay attention to this the magnetic field. Okay, and yeah, this Zeeman effect only is observable in the presence of magnetic field. Okay, uh, from the general chemistry, you already learned the four quantum numbers. Okay, four. What is the what are they? The principal quantum number n. Okay, n starts from 1, 2, 3, 4. Okay, when n is 1, that is 1. That's the principal quantum number, and there is a K shell. Okay, and another quantum number is L. Okay, L is what? Azimuthal quantum number. Okay? L starts from 0, uh, 0, 1, 2 up to n. Okay, and another third quantum number is magnetic quantum number. Okay, ML symbol is ML. ML is minus L and minus L plus 1, and then 0 and 1, 2 and up to L. Okay, if you are not sure, you go back to the general chemistry textbook. Okay, and the final quantum number is a spin quantum number. Okay, electrons have spin. Oppositely. The spins with opposite direction. Okay, it is usually up spin or down spin. Or spin quantum number is either 1/2 or minus 1/2. Okay, but now is the Zeeman effect is visible in the presence of magnetic field. Okay, here look at that. This is the electronic energy level 1s and 2p, for example. Okay, and without magnetic field, this 2p, this energy level is degenerate. Okay, that means actually p, yeah, p is L is 1, so ml is minus 1, 0 plus 1. Okay, it's not split. Okay, it is a degenerate. Okay, and then transition from 2p, this is emission. Okay, 2p to 1s is possible. Okay, in this case L is 1 and ml is plus 1, 0 and minus 1. Okay, and the energy level of the 2p minus 1 equals 2p 0 and 2p plus 1. Okay, yeah, but when you apply the magnetic field, this 2p energy level split into 3, 1, 2, 3. Okay, the middle one, it doesn't change, but there is this, this is quite exaggerated, but this energy level one is a little bit what goes up, and the other one is goes down. Okay, so here, so these degenerate energy levels are split into 3. Okay, in the presence of magnetic field. Okay, and here in this case, ml plus 1, 0 and minus 1 are all is split. Okay, so here this energy level 2p plus 1 is slightly higher than p0 is higher than p minus 1. Okay, yeah, how do we apply this Zeeman effect to correct the background? Okay, here is the idea. Okay, look at that. This is the spectrum relative signal. Okay, from the atomic emission. But when you turn off the magnetic field, you observe this signal, and this signal contains sample and background as usual. Okay, when field is off, but when you field on, okay, and this part, okay, is removed. Why? Because only background signal is detected in the presence of field on. Okay, so here background signal, you look at that, this one, this middle part is observed. All right, so no, the other part. Okay, the middle part is not absorbed, only the other part is absorbed by that's the background. Okay, so to get true signal is what you subtract, this background signal from the sample and background. Okay, yeah. Okay, here sample and background are observed when the field is off. Okay, here it contains background, so background alone is absorbed when the field is on. Okay, the difference is the corrected signal. Okay, yeah, this is the Zeeman correction, but you need to buy this very expensive instrument, okay, to use this Zeeman correction. Okay, and so instrument is very expensive. When a magnetic field is applied parallel, this is important, parallel to the light path through a furnace, the absorption or emission line of the unlighted atoms is split into three components. Two are shifted to slightly lower and higher wavelengths, and one component is unshifted. Okay, the unshifted component does not have the correct electromagnetic polarization to absorb light traveling parallel to the magnetic field and is therefore invisible. Okay, yeah. So idea is to you take the signal in the presence, in the absence and the presence. Okay, yeah. And the difference is the correct signal. Yeah, and this correct signal remove doesn't contain the background. Okay.